Part 2 System Operation Schematic. System Operation Schematic is the second in a series of videos which are intended to explain why the buoyancy engine could be useful, how it works and why it makes good business sense. These include an introduction to tidal power, a scaled application, an illustrated business case, construction challenges and frequently asked questions. Here, the storage vessel incorporates a matched turbine and generator set which are rated to suit the working head of water during the generation phase of the operation cycle. The dipstick shows a tidal range of 2 meters with half-meter graduations. The ratchet pulley system connects the storage vessel to the pontoon, and for this example a 6:1 gearing ratio is shown. In simple terms, the storage vessel will descend by 2 meters, the tidal range, multiplied by the gearing ratio, in this case 6, to give 12 meters descent travel, each time the water level rises from low to high tide. For demonstration purposes, I've only shown a single pulley system, but in practice there will be several compound pulleys, each operating together, as shown in the scaled application video. When the pulley is coloured red, it is fixed. When blue, the pulley is driven by a motor to take up cable slack, and if grey, the pulley is free to rotate. The optimum business case is achieved by selecting a deep water location with a good tidal range and selecting a pulley gearing ratio to complete a full operating cycle with each tidal cycle. The UK is ideally located on a continental shelf which provides adequate ocean depth and good tidal range within easy reach of the coastline for cost-effective connectivity to the national grid. To contrast against an ideal arrangement, this schematic animation depicts 3 12-hour tidal cycles for one complete operation cycle, including 6-hour descents and 6-hour generation phase. The rest of the time is taken up waiting for low tide and a purge phase to empty the storage vessel. This would give 2 generation phases every 3 days or 6 tidal cycles, and could be used singularly to top up the national grid at peak times. Alternatively, a base load can be met continuously by adding further buoyancy engines operated in a staggered formation. Each switch represents a separate buoyancy engine, that is, when a switch is closed, one of the 6 buoyancy engines is generating power. Power generation is achieved when valves are opened to allow a flow of water across the turbine. The turbine and the generator are linked by the same axle, so when the turbine rotor turns, so does the generator rotor to generate electricity. The greater the flow rate and working head of water, the greater the power which can be generated. There is a great improvement in controllability when compared to wind turbines that only generate power if the wind conditions meet certain criteria. Similarly, solar PV systems only generate power during the daytime, and even then there's a significant drop in performance if it's cloudy. This doesn't mean these technologies can't serve a useful function. In fact, the buoyancy engine pontoon would provide an ideal platform for offshore wind or solar PV to augment the business case. The turbine outlet pressure also affects working head, and to optimize efficiency there is a vent pipe, not shown, running from the storage vessel to the surface. The vent pipe is sized to relieve the build-up of pressure that would otherwise occur within the storage vessel as it fills. Unfortunately, due to the rise in water level within the storage vessel, a small reduction in working head can't be avoided. The storage vessel is engineered to remain buoyant even when full of water. Once the generation phase is complete, the storage vessel is allowed to ascend due to buoyancy. In order to avoid take-up losses or excessive drift, the storage vessel isn't allowed to break the surface, but instead is held just below, where it is then pumped out with a purge pump. Since the working head during the purge cycle is much less than that during the generating phase, much more energy is produced than is used during the operation cycle. The illustrated business case will run through a worked example and serves to show the importance of the feeding tariff and renewable obligation certificate government incentive schemes which encourage investment into new renewable technologies such as this by ensuring long-term revenues. The next video in the series is a scaled application video which is based on 3 buoyancy engines, each with a turbine and generator set rated at 2 MW. The systems are based on a 25:1 pulley ratio, 2 metre tidal range and 50 metre working head with a storage vessel capacity for a 4-hour generation phase. For the UK there are typically 2 tidal cycles per day, so each buoyancy engine would provide 2 generation phases of 4 hours or 16 MWh of power per day. This provides 48 MWh of power in total per day, which is enough to power 5,800 smaller homes or 3,600 average sized homes.